may recognize that as the song that you hear on the Peanuts, Charlie Brown. That's called Linus and Lucy. Kind of a fun little song to play on the guitar where you got two things going on at the same time, just like on the piano. Okay, so I hope you enjoyed that introduction. What we're going to be looking at is motion. We're going to be talking about derivatives and how they relate to a rate of change. So we're going to do a lot of physics in this section and then wrap it up with a little bit of economics. So to begin with, one-dimensional motion, you can think and plot motion on a number line. So let's just say you're traveling in a straight line, and the idea would be, well, that wasn't much of a number line. Let's try that again. What's going on? Okay, there's a number line, much better. Okay, so let's just say, for instance, that you have some time, t equals 0, you can represent that as your position. And then let's say, 2 seconds later, then you have a different displacement. So right here we'll say, okay, the displacement is 0 at the beginning, and right here after 2 seconds we will say that we went, say 5 meters, okay, in that 2 seconds. All right, so that you can plot out a one-dimensional motion like this. And then let's say we have another time. Let's say that we have a time that is like 5 seconds. And after that 5 seconds, you have displaced, say, 15 meters in that time like that. So you can represent motion in that way on a number line, and you can do an average rate of change, and ultimately we could figure out an instantaneous rate of change. So an average rate of change, remember, is just a slope. So if you had 2 points, if you had like the point at 2 seconds, you went 5 meters, and say that you had another point where you went after 5 seconds, you went 15 meters, then you could find that average rate of change just by doing the slope. So you'd have 15 minus 5 over 5 minus 3. That would be 10 over 2. So that would be 5 meters per second would then be your average rate of change on that. So you can represent motion in that way. Okay, and this formula right here is going to be building the difference quotient. So you have a displacement. So delta S just means your change in position. And that change in position is found by subtracting these two things. So if you have the function a plus delta t, that just means after a amount of time, that position A, you're going to subtract those two displacements like that. That's no different than what I did here. I basically, when I did an average rate of change, I did the change in displacement, which would be 15 minus 5. And that doesn't give the slope, but that gives the rise when you're doing your average rate of change. So that's what that part of the formula says then. Okay, now an instantaneous rate of change, the only difference on that is that's going to be a slope of a tangent line like we've talked about. So now when you do an instantaneous rate of change, you're getting the velocity. And what that velocity is going to be doing is you're going to be doing the change in s over the change in time. Okay, and that's what I did on this average rate of change. That was an average velocity. I did delta S is the change in displacement, 15 minus 5, and then delta T is the change in time, where I had the 5 minus 2 seconds. But if you want to find an instantaneous rate of change, then what you're looking at is you're going to look at the limit as delta T goes to 0 of the difference quotient. So you really have the rise over the run, which is calculated like that. So see, that gives the difference quotient, and then that's the same thing as f prime of a, which is what the velocity is equal to. So it's an instantaneous rate of change. Okay, so we're going to be talking about this more specifically in this section as how it relates to derivatives. Okay, so down at the bottom, this is kind of what I was trying to go through. This is your average velocity right here. And again, that's the difference quotient. you're subtracting the positions and dividing by delta t, which is some distance between the times, like that. So I did an example of that when I did, 2 seconds you displace 5 meters, 5 seconds you displace 15 meters. Calculating that slope is finding that average rate of change. Okay? All right, now when you do an instantaneous velocity, that's an instantaneous rate of change. So now what you're doing is you're doing a limit as delta t goes to 0, like that then, and that gives you your derivative. Right, so I'm going to pull up a couple of applets, and I'll just kind of go over visually what we're doing here. We've talked about this a lot this semester, I know already, but it's good to kind of review this as we're learning this in a little bit different way. So when you're doing an average rate of change, that is a slope of a secant line. You have 2 points. And notice as these 2 points move closer together, that slope changes. Okay, the rise over run changes, so that average rate of change is changing throughout this. And it can be negative too. So if I move these points like this, then I have a negative slope, so I have a negative average rate of change. Right, so that's what average rate of change is. It's a slope. And I also want to review instantaneous rate of change. Just pull up this Desmos app real quick and show you how this works. So the idea with this is, I'm going to change this a little bit. So let's just say you have a constant function like 4. Well, the average rate of change on this, we're going to look at an instantaneous rate of change. We know the slope of this tangent line to a horizontal line 0, and that's not going to change at all on this. No matter where I move these points, that average rate of change is always 0. Okay, so we've got that. And then if I make this into a linear function, like say 4x, well, I've got a slope of 4. You know you have a slope of 4 because that's linear. And again, it doesn't really matter where you are on that. As h gets closer and closer to 0 in this difference quotient, you're still going to have a slope of 4. Now, when you get into like a quadratic, okay, this is where it changes a little bit. The slope of the tangent line is changing constantly. So again, an average rate of change, you have 2 points, but as these 2 points get infinitesimally close to each other, then you get close to the instantaneous rate of change. So right now, these are 2 separate points. That's given a slope of 4.2, but as I get closer and closer and closer, that slope is going to approach the value of the instantaneous rate of change, which is 4. If you did the derivative of x squared, you would get 2x, and if you plugged in x equals 2 into the derivative, you would get 4. So that's the idea on that, is those points get infinitesimally close. That slope gets close to 4, which is the slope of a tangent line. Okay, so that's the idea. All right, so I want to go ahead and close this, and we'll go back, and then we're going to look at an example that I think will help you to make good sense of what we're doing with motion here. So what this is you can actually plot like your trip on a coordinate plane. This is just basically showing that a airliner is doing an out and back trip from Seattle to Minneapolis. S equals F of t is the number of ground miles from Seattle, T hours after a takeoff of 6 a.m. Okay, so we're going to answer several questions about this then. And to begin with, let's just kind of, make a few notes to ourselves. Right there, 6 a.m. is when we take off. And then 8.5 hours later, so if you go 6 plus the 8.5 hours later, you get 14.5, which is really 12 noon plus 2.5 hours would be, you get at 2:30. So right here, that point right there is going to be 2:30 p.m. Okay, after you've gone through that 8 hours, 8.5 hours like that. Okay, so we're going to answer several questions about this. So what we're going to be looking at is, just get in mind that this is the displacement. So for instance, at 7 a.m., you have gone about 300 miles from the airport. at, this would be 8 a.m., you have gone about 1,000 miles from the airport and so forth, okay? And that's what that means. And then at 2:30, your displacement is 0. That just means you're back to the original starting point right there. So round trip, you're coming back to a displacement of 0. So we're going to calculate the average velocity of the airline during the first 1.5 hours of the trip. Now, when we're doing average velocity, you're doing a slope, so we need to know 2 points. So the first point is going to be at time 0. We haven't moved yet, so that's a displacement of 0, so we have that first point. Whoops, I need to write this right here. So I've got that. Okay, then at 1:30, we're doing the first 1.5 hours of the trip, so we're here. So go up to the function. That looks like that gives you a point. After 1.5 hours, that looks like you have displaced 600. So your second point that you get is a time of 1.5 hours and a displacement of 600. So what you're going to do is you're going to do the average velocity, which is really just a slope of a secant line. So we're going to do the change in the displacement over the change in time. So the displacement would have 600 minus 0. The change in time is 1.5 hours. So you end up getting 600, and that would be in miles over 1.5 hours. And then you can calculate that on your calculator. 600 divided by 1.5 is 400 miles per hour. So that would be your average velocity during that first 1.5 hours of the trip, okay? All right, the next thing it says is find the average velocity between 1:30 and 2:30. Okay, so 2:30 is at the end right here. 1:30 is right there. Okay, so that right there is 1:30 p.m. 6 p.m. is noon, by the way, so we got that. And just find what that point is. So it looks like that point would be after 7.5 hours, your displacement now looks to be 200 miles approximately. I don't know, I might change that a little bit. Let me zoom on that a little bit. I think it's more like, maybe like right there. I'm just going to say that it's this point right there, and then that would be about 300. So I'm looking at a point of 7.5 hours. You have your displacement now is your 300 miles away from the airport that you're returning to. And then 8.5 hours, your displacement is 0. So what you're going to do is you're going to work out using those 2 points, 7.5, 300, and the second point, 8.5 and 0. So you do a slope of a secant line, which is delta S over delta T. So find the change in displacement and be consistent in the order you subtract these. So I'm going to go 300 minus 0. And then the change in time, I'm going to subtract it this way. You could do everything backwards and get the same answer. So this is a displacement of 300 miles. And then that was -1 seconds. Okay, like that's just a negative number. Time is not negative, but you're going to get a negative slope out of this. So you basically get -300 miles per hour is going to be your average rate of change or your average velocity on that time period then. Okay, so if you're finding average velocity, you're looking for 2 points. The x value is really your time, and the y value is your displacement. And you can have a negative average velocity. This just means the direction is you're going to, and this direction here you're going back. So you could think of maybe you're going north here, and then maybe you're just changing directions and going south there. So you're going in an opposite direction. Okay, the next question on this is that what time is the velocity 0? Well, you would have to have an average rate of change of 0 on that. So that means your slope of your secant line would have to be 0. So if you look at places where the slope would be 0, that appears to be in this interval right here. Okay, so from there to there, it looks like your velocity is 0 because the slope of that secant and the slope of the tangent line of every single point in there is equal to 0. Okay, so what we would say on that is that would be after 3 hours and after 5 hours. So we start at 6 a.m. So basically after 3 hours, you would be 9 a.m. And then after 5 hours, you would be at 11 a.m. Okay, so basically between 9 a.m. and 11 a.m., then you have a 0 velocity. Well, what is the plausible explanation? Well, it means you've landed at the airport and you're not moving. Okay, so you're basically not moving. You're at the airport. You're not ready to take off in your return journey. So that's what that would represent then. Okay, so as you look at this, the idea is your average velocities are positive until you get to the airport. Then you have a 0 velocity when you land, and then your velocity becomes negative because you're doing a return trip. That's the idea. Okay, so let's see. We're going to determine the velocity at noon, and we're going to explain why the velocity is negative. Okay, remember we start at 6 a.m., so basically 12 p.m. would just be 6 hours later. So in this case, time would be 6. So if you look at your graph, you have this point right here, 6 hours. It looks like your displacement is 1,200 miles like that. So what we're going to need to do is we're going to try to determine the actual velocity, the instantaneous velocity, not that. So what we have to do is we have to find another point that we know the values of that would make what looks like a good tangent line there. So the way I'm going to use this is I'm going to use the point 6/1200. Then I'm going to see if I find another point. See, the slope of the tangent line right here is going to look kind of like that. So in this region here, it almost looks like that slope's pretty constant. So I'm going to use this second point, which is 7, and that would be 600. Okay, so that's just a good point to use on this. So the second point for estimation I'm going to use is 7,600. Okay, and I'm doing that because if I connect those two dots, that looks like that would be about the same as the slope of the tangent line. So your slope of your tangent line would be like that. That seems like a good estimation then. Okay, so we go ahead and do our slope. So what we're really doing is we're doing a slope of a secant line to estimate the slope of the tangent line on this. Okay, so again, we can do the change. I'm going to go 600 minus 1,200 for my displacement. Then I'm going to do the change in time like I've been doing. So that's negative 600 miles over 1 hour. So you end up getting, this would be your velocity there, okay? So why is it negative? The reason that it's negative is because you are returning to the airport, okay? So it's a return trip, so your direction changes. So you're going in a negative direction. So that's the idea. Okay, so that's kind of a good problem to help students make sense out of a graph of displacement and something you can relate to like an airport and a trip like that. So what I'm going to do is I'm going to have you go to the next page. If you need to pause the video right here, you can go ahead and do that now. But I'm going to have you go to the next page. And what I'm going to have you do is work this similar problem out, answering the questions, and then go ahead and pause the video. And then when you're done doing these problems, I'll display that like that. When you're done with those problems, then I'll have you resume and check your answers. Okay, so let's see how we do. Okay, so here's the answers that I'm displaying. Let's go over this. If you can go ahead and pause the video and you can check your answers. If you got them right and understand that, then you can move on. Otherwise, you can watch as I go over kind of an explanation for that then. So basically, this says that you leave the station at 9 a.m. So that point right there is 9 a.m., and that's when the time is 0, and you have a 0 displacement. So that's your time. This is your displacement S like that. So you're determining the average velocity for the first 45 minutes. And let's see, these things go by 0.25s. So that would be half an hour. This would be 0.7 right there. And that's a point that has a time of 0.75 and a displacement of 30, and that's miles. Okay, so it does say that's miles. So again, what I'm doing is I'm doing the slope between these 2 points. I'm doing 30 minus 0 over 0.75 minus 0. Work that on the calculator. Again, you're just doing delta S over delta T. That'll give you the average velocity during the first 0.75 or 45 minutes of the journey. The next thing is we're going to do the average velocity from 0.25 to 0.75. So we have this other point here. We have a point 0.25, and that looks like that has a displacement of 10. So again, I'm taking these 2 points, 0.25, 10, 0.75, 30. I'm finding the average velocity, which is a slope. Again, it's doing delta S over delta T. So I just do the slope like I've done here. That gives me 45 or 40 miles per hour like that. Now the question says, is this a good estimate of the velocity at 9:30? Well, okay, so at 9:30, you would be here. So the velocity would be the slope of this tangent line. And if you look at the slope of the secant line, they look like they're about the same. So that is a good estimate for the exact velocity you would be doing at 9:30. So that's the idea. Okay, part C says find the average velocity of the car over the interval 1.75 to 2.25. So let's see, at 1.75, looks like you get the point time 1.75, displacement of 15 miles. And then the second point would be 2.25, which appears to be there. So that is 2.25, comma, negative 15. Okay, so I've got these 2 points here on part C. Again, I do the slope. You can kind of choose the order. I'm doing delta S over delta T, so I'm doing 15 minus negative 15 over 1.7 minus 2.25. That gives negative 60 miles per hour. Okay, and the reason for that is because we've changed directions. See, basically right here on this problem, you're going north here. Right there, your displacement is north there, and then you're changing directions. What happens here is at this moment in time, the slope of the tangent line is 0, so that means, okay, you've come to a stop, then you're returning like this. Okay, so you're basically going south there, and then for this brief amount of time right there, you start going north again. So that's how you can see how the directions change on that problem. Okay, so keeping that in mind on the last problem, we're describing the motion. So the way I look at it, I highlighted in yellow for the first, it looks like for the first hour of the journey, that would be 9 to 10, you're going north. Then you reach that peak where the velocity is 0. Then it looks like from time equals 1 all the way to 2.5. So that would be 10 a.m. This would be 11:45. You're going south. And then for this brief time here, from 11:45, noon would be at 3 o'clock, or 3 hours. So it looks like from that, you're going back north, so you're heading back towards the station. Okay, you don't reach the station because you would have to be back at a point where you have an x-intercept, like that. Okay, so that's the idea. If you do that correctly, that'll help you understand how a position function can be plotted. Okay? All right, so I'll go ahead and move to the next page here, and we're going to begin to kind of look at the calculus, working with derivatives, and that kind of thing next here. Okay, so now we'll begin to look at velocity, speed, and acceleration, and how these things relate to a rate of change in calculus. So it goes like this. S of t is our position function, like the last two examples we used. That is your displacement. That's how far you are at any point of time from the beginning of your journey. So the velocity is the first derivative, ds over dt, or s prime of t. That gives you the first derivative gives velocity. Speed is different than velocity. So velocity, basically, it can be either negative, positive, or zero. You can have negative velocity like we saw, but speed can only be positive or zero. You can't have a negative speed. That's why the absolute value of the velocity gives you your speed. So if you're driving in a car, your speedometer is not measuring velocity, it's measuring speed. It's always positive. Your speedometer never displays a negative number. Okay, well, acceleration is telling you how your velocity is changing. Are you speeding up? Are you slowing down? Your velocity when you travel in your car is constantly changing. Right? So the acceleration, sometimes you go a little faster, sometimes you slow down. So it is the second derivative. It's another rate of change. So the second derivative is going to give you your acceleration. Okay, so a couple of things on this. Velocity, like I said, is positive, negative, or zero. The units are distance over time, so that could be meters per second, foot per second, miles per hour, that kind of thing like that, kilometers per hour, and so forth. Speed is the absolute value of velocity, so speed is positive or zero. And the units for speed are distance over time, meters per second again, just like velocity. Acceleration is the rate of change of velocity, so it can be positive, negative, or zero. And then the units for this should be acceleration. I didn't type that right. So the units for acceleration are a distance over a time squared. Okay, so you could have like meters per second squared like that. Okay, so just a couple of things on this that you typically learn in physics, like the acceleration due to gravity. If you neglect air resistance, if you drop something from a tall building on Earth, the acceleration is either 32 feet per second squared, or in the metric system, it's 9.8 meters per second squared, like that. Okay, the reason you have that second squared is because you're doing another derivative. Okay, so that's what forces that to be a second squared. Okay, so down at the bottom, this kind of relates a function and the graph of its derivatives. We've learned how to graph derivatives, so it's important that you kind of make an important connection on this. So this is your position function, and the velocity is just the derivative. The derivative of t squared minus 5t is 2t minus 5. So that's the velocity, that's the graph of its derivative. The acceleration is the second derivative. So the derivative of 2t minus 5 is 2. So in this case, if you graphed out a equals 2, you'd have a horizontal line. So you want to make a connection on this and how this works then. So thinking about how this goes, okay, first of all, this is quadratic, this is linear, and then this is constant. Okay, that's because we're doing derivatives, and if you had something like x squared, then you have 2x, then you have 2. So you have a quadratic, then you have a linear when you do the first derivative, and then you have a constant when you do the second derivative. A few other things I want you to note on here, though, too. Right here, at this point right here, that looks like at 2.5 seconds, the position, the slope of the tangent line, right here, the slope of the tangent line right there appears to be 0. So notice when we graph the derivative at 2.5 seconds, the value of that derivative Again, it's the slope of the tangent line is 2.50. And then what happens here on this interval here, you have negative sloping tangent lines. So if you have negative sloping tangent lines, that means you're going to be below the x-axis. All of these y values are negative, and the y value is the slope of a tangent line. So what you would find is right here, at 1 second, the derivative would be about -3. The slope of the tangent line right in here would be -3. Okay, and then what you get into past that is now you have a positive sloping tangent line. So that means the graph of your derivative is above the x-axis. Okay, like that. Okay, so again, if you were at 4 seconds, the value of that derivative would be some positive number. It looks like it would be about +3. Okay, so that's what you're doing. And then what happens on this is the slope of the tangent line on the velocity is always constant. So like if you take any point on this linear velocity, and if you count out the slope, okay, it is 2. It's kind of hard to see on here, but if you went up 2 over 1, you would be on the graph. So this thing just has a constant slope of 2. So if we graph that constant slope of 2, we get a constant function. So you want to think about how these derivatives, graphs of the derivatives, relate to what we're doing. Okay? Okay, so let's move to the next place here. We'll do some examples of how this works out now. Okay, so this is kind of applying what we're learning now. So this one, it says that you have a stone that's thrown vertically from the edge of a cliff on Mars. It has an initial velocity of 64 feet per second. You're throwing it from a height of 192 feet above the ground. Then the acceleration due to gravity on Mars is 12 feet per second. It's lower than the 32 feet per second squared that's on Earth because it's a less massive planet. And then the height s of the stone above the ground after t seconds is given by this position function. So this is giving you the position of the stone at any instant in time. Okay? When you're in physics, you learn about a formula that puts all this together for you. And it goes like this. It goes like S of t, you all don't have to know this formula, but it's -1/2 of the acceleration due to gravity, t squared, plus the initial velocity, plus whatever that initial height is. So what happened on this problem is the acceleration due to gravity is 12, the initial velocity was 64, and the height was 192. So when you put this together, you get half of 12 is -6, plus 64t, plus 192. You don't have to know this formula, but that is something that you typically talk about in physics classes when you're talking about motion. Okay, so determine the velocity after t seconds. Well, the velocity function, it is a function, it's just the first derivative. So we go ahead and do the first derivative of this function. That would be -12t plus 64. Of course, the derivative of the constant is 0, so this would be your velocity function right there. Now what we're going to do is answer several questions about this situation. So this says, part B says, at what time does the stone reach its highest point? So this is a parabola. See this, if you graphed this function, it would be a parabola going upside down. Remember, the velocity is a slope of a tangent line. So what happens when you reach the peak, the value of that derivative is going to be 0. So the stone will reach its highest point when that velocity is 0, because velocity is a slope of a tangent line, and it's 0 at that peak. So what we do is we need to take the velocity, and we need to set that equal to 0. Okay, so we're going to solve this equation. The Velocity is negative 12t plus 64. That's equal to 0. Okay, we're going to solve the equation, so you could subtract 64 from both sides. You could divide by negative 12. And when you do that, you get t is equal to, and I'll have to pull up my calculator on that one. I think we'll probably round this one off. Okay, so it looks like we have 64 over 12, and then we'll just round this off to maybe just one decimal. So we'll just say 5.3. Okay, so that happens at about 5.3 seconds. Okay, so that would be when that happens. All right. Next thing it says, what is the height of the stone at the highest point? Okay, well, what we did is the highest point, we just figured out when that happened. The highest point happens at t equals 5.3 seconds. Okay, so what we do is we plug into the position what gives you the height. So we have to do s of 5.3. Okay, so we're going to do negative 6 times 5.3 to the second plus 64 times 5.3 plus 192. And need to just put that in a calculator here. So let's see, negative 6 multiplied by 5.3 to the second plus 64 times 5.3 and then plus 192. And this will give us what that height is. So that's about, we'll just round that off to one decimal. That's about 362.7 feet is about what the height of that is. So if we know the position function only, we can figure out all kinds of things about this indirectly with just using mathematics. Okay, so that's how you would crunch that out. Next question is, it says, when does the stone strike the ground? Okay, now remember what this is this is a parabola. And when it hits the ground, s is going to be 0. Because s represents the height above the ground, so that's s equals 0. So the stone strikes the ground when the height is 0. So what we have to do is we have to set the position function equal to 0 and solve that equation. And this may require a quadratic formula, which is no big deal. So the displacement is negative 6t squared plus 64t plus 192. That's equal to 0. Now you could go straight to the quadratic formula if you want to. That's totally up to you. Or what I like to do is, if I can divide everything by a number, then I like to just, get rid of everything. So I'm just going to divide by negative 2. I'm going to divide by a negative, but you don't have to. You don't even have to do this. So if I do this, I would get the equation, the quadratic equation, 3t squared minus 32t minus 96 is equal to 0. Okay, and what I can do from here, of course, is a in the quadratic equation is a is 3, b is negative 32, and c is negative 96. So let's go ahead and just do this with the quadratic formula then. So the quadratic formula is, we're solving for s here. Okay, so the quadratic formula is negative b plus or minus the square root b squared minus 4ac all over 2a. So you want to write that down. And then we'll go ahead and just work out the arithmetic and use our calculator to help us through this, though. So plug in your numbers. A is 3, so you get negative 3 plus minus b squared, which would be negative 32 squared, minus 4 times a times c. I got all over 2 times a, like this. And let's work with this on our calculator, and let's see kind of where this takes us then. So let me pull up my calculator. What I usually like to do on my calculator on something like this is just do the discriminant. The discriminant is the part under the radical. I'm just going to do that in one step. So I've got negative 32 raised to the second power minus 4 times 3 times negative 96. And we'll record that. That's 2176. So I'll put this over here then. Okay, so it looks like what we got is we have, this is equal to negative 3 plus or minus the square root of 2,176 all over 6. Now what we got to do is we need to use our calculator. We got to do this in two directions, okay? So what this is doing then is, what we're doing is we're finding a time. This is a time that we're looking at. We're finding when the stone reaches the ground. So we need to do two things. We have negative 3 plus square root of 2176 over 6. And then we also need to use our calculator to do negative 3 minus the square root of 2176 over 3. And one of these answers is not going to make sense. So we'll kind of talk about that. So I'm going to put this in, negative 3 plus square root of 2176. Get that answer, divide that by 6. That will give a time there, which is approximately so I was looking at my work and I made a mistake. You guys probably may have caught that while I was doing this. I don't know why I put a negative 3 there. Negative b is 32. So let me fix this. I apologize for that. I do stupid things like that sometimes. Let's get this fixed. Okay, so we have negative 32. So we should have 32 like that. Okay. Now I think I'm good. All right, so let me fix that then. Okay, I'll clear that then. So we have 32 plus not that, come on. 32 plus square root of 2176. I'll just get the answer to that. Divide that by 6. So this gives us about 13.1 seconds, which seems to be a logical answer. And then if I do the next one, this is nonsense. And I can see it gives a negative number. I mean, if you do 32 minus the square root of 2176, you get a negative number. Then if you divide that by 6, you get a negative number. So you can't have a negative time. So that one gets thrown out. So this would be the answer to that problem. Okay, so it takes 13.1 seconds for the stone to strike the ground. Okay, so we have that now. Okay, so the next thing says, with what velocity does the stone reach the ground? So we just figured out at t equals 13.1 seconds, the stone reached the ground. Okay, so what do we do? Remember, the velocity is the first derivative, and we got that in part A. That's negative 12t plus 64. So if you plug in the velocity of 13.1 seconds, you work out negative 12 times 13.1 plus 64. And you can work that on the calculator then. So let's see, we have negative 12 times 13.1 plus 64. And that will give me about negative 93.2 feet per second. Okay, if you read the problem, it told you that the units were, the displacement was in feet and the time was in seconds. Okay, so why is it negative? Okay, because it's going down. Okay, you can think of it as in the down direction. It's reached its height, now it's going down, so the velocity is negative for that reason. Okay, so that kind of wraps up the problem. A good thing to do on problems like this is to be able to verify everything you do on your graphing calculator. So we're going to do that, and we're going to look at kind of a verification of what we just did here. Okay, and we're going to construct a graph on this. Okay, so let's go ahead. I'll pull up my calculator, and we're going to graph the displacement. So we have -6 x to the second, have to use x of course, plus 64x plus 192, like that. Now we don't want to do a standard window. Let's just kind of look at what we came up with here. So we reached the ground at 13.1 seconds. So to me it would be rational to go like this, go 0 to maybe 14, scale that by 1, and then the maximum height, we figured out the maximum height on this was 362 feet. So let's do this. Let's go for the y's. Let's go 0, which would be the ground. Let's go 400 feet, and then scale that by 100 like that. Okay, so this right here will give you a kind of a nice viewing window. Okay, then I'm going to graph this, and then we'll kind of talk about what all these things on the graph meant then. Okay, so I'm going to go ahead and move my graph over here, and I'm just going to have you sketch this graph that I'm dragging over here, and just label a couple of things here, a couple of key things here. So basically what we have here is, this is like, let's see, this is going by ones, so we found that it reached its maximum, it reached its highest point at 5.3 seconds. So 1, 2, 3, 4, 5. Notice at 5.3, that looks about right. That's the highest point right there. Okay, and then it reached the ground at 13.1 seconds. So here's your time in seconds, and then your height is just going up to 400 like that. I don't think I scaled the x-axis, but I should have. I think I added an extra 0 in there, so it should go like that actually. So that's a better graph like that. Okay, so that's kind of what we found in the problem. Now let's verify several things on the graphing calculator to just kind of help us make sense of this. One thing that you can do on here is, let's see visually if the maximum height happened at 5.3. So if I trace at 5.3 seconds, that looks like it's on the height. Notice that that height is 362.7 is what we rounded that to. So that looks like that's rational. And the other thing we found is what happens at, if you trace at 13.1, that's when it reached the ground. Well, that's close to 0. So again, that was only an estimation. So that also right there tells us that we're on the right track with getting the answers to this problem. Okay, so I just want to note those graphs on there that verify some of the key things that we learned on here then. Okay, the other thing on this is just a couple other key things on here is, you know, this right here is the original height of 192 feet. The maximum height there was about 362.7 feet like that, and your velocity is positive, then it becomes 0, then your velocity becomes negative. And it's speeding up as it goes down to the Earth, or down to Mars, or wherever we are on this problem, like we're on Mars, because the slope's getting steeper. See, that slope gets steeper, that just means it's picking up speed. Okay? And if you went to Mars, where there's very, very little atmosphere, so there would be very little resistance, you could really test out, you know, the fact that you can test out that acceleration due to gravity. I think when humans went to the moon, on one of the moonwalks, they dropped a hammer or something like that and measured there was an experiment that they did on the moon. Somebody dropped a hammer and a feather at the same time, and they did drop it exactly the same time, unlike Earth, because there's no air resistance on the moon because there's no atmosphere. Okay, so that will kind of wrap that up. Now I'm going to have you go ahead and go to the next page, and I'm going to let you do a problem and work through this. See if you can kind of repeat some of the ideas that I did. So let's go ahead and pause the video, and when you come back, we'll check answers and see how we did. Okay, so I'm going to go ahead and display the answers. If you want to pause your video again, look over this, see if you got right answers, correct anything you got wrong. If you do understand all this and feel like you got everything right, then you can move on to the next part of the video then. Okay? Okay, so let's kind of look over this then. So you got this position function. We're only interested from 0 to 4. And so we're going to do the velocity function, and we're going to find the velocity after 1.5 seconds. So the velocity is the first derivative. And let me zoom on this so I can see this a little bit. So the derivative would be negative 18t squared plus 72t minus 54. Just evaluate the velocity at 1.5. Working out the arithmetic, you would get 13.5 miles per second. All right, so finding velocity is very simple. Just find the first derivative of the position function. Okay, then you're going to find the acceleration at t equals 3 seconds. Okay, so the acceleration is the second derivative. So the second derivative would be negative 36t plus 72. Okay, I'm just doing the derivative of the velocity. Then I'm going to evaluate at 3. So I plug 3 into the acceleration. I end up getting negative 36 miles per second squared. The units on that will be miles per second squared. Okay, because I did give you miles and I get time in seconds like that. Okay, next part of the problem is when is the velocity 0? So we found the answer to the velocity in part A. We need to set that equal to 0, and then you have to solve this equation. Now you could go directly the quadratic formula on this if you wanted to. I noticed that I can factor a negative 18 out, so I factored out negative 18, and then this factored further. Factoring is usually a little bit less time intensive than the quadratic formula, but you can do either one on this problem. So when I factor this, I end up getting this. Set each factor equal to 0. I get t is 3 seconds, and t equals 1 second. So there's actually 2 times when this graph hits a velocity that's equal to 0. Those kind of be peaks in the graph. Okay, peaks and troughs. You can have a high point and a low point. Okay, the next one says, when is the acceleration 0? Well, the acceleration we got in part B, so set it equal to 0. Solve this equation. Okay, the acceleration is negative 36t plus 72. Solve that equation. The acceleration is 0 at 2 seconds. Okay. Then it says, when is the acceleration positive? That means take the acceleration, solve the inequality, set it greater than 0, solve this equation, you will get less than 2 seconds. Okay? Now, it's not going to be negative, so notice on this, if I write this in an interval, I need to say between 0 and 2 seconds. Okay? So that's when your acceleration is positive. Okay, and then to finish it up, it was just kind of doing the graphing. So I graphed this on my calculator. And let's see, I used this viewing window here. So in the problem, they said, we're only interested in 0 to 4. So you could have graphed it 0 to 4. I decided to go ahead and take it to 5. And I did my window, I think, like negative 100 to 100. Kind of like that on the calculator. And so what we're trying to do is determine where the velocity is positive and where it's negative. And a lot of people might not have known how to do this. I wanted to just on the video give you a chance to see if you knew how to do that or not. And this is something that you'll do in a calculus class from time to time is you'll do sign charts. So you're solving what we call an inequality, a quadratic inequality. So your velocity is this. Remember, we figured out where the velocity was 0 as 3 and 1 seconds. So what we do is we do a sign chart for 1 and 3 seconds. And we also want to really start this thing at 0 like this. You don't want to go into the negative numbers, so we just kind of look like that. And there's basically 3 intervals. There's between 0 and 2. There's between 1 and 3. And then there's 3 to 4, really. I mean, I think probably they wanted you to end this at 4. So you probably would want to use a different test point than I did here. But this works fine if you do this then. So the idea is, on this problem, is just plug in some test points. I just ignored the 0 and 4. It didn't really make any difference on the problem. So what I do is I'm going to plug test points into the factored form of the derivative. You can also plug it into the non-factored form of the derivative. So I said, okay, let's pick a point less than 1. So I picked 0. I probably would have been wise to have picked something like 0.5 instead. If I did, the thing is, if you plug that in, you're going to get a negative answer, meaning that velocity is less than 0. Okay, then pick a test point between 1 and 3. I picked 2, so I did negative 18 times 2 minus 3, 2 minus 1. I worked it out, I got a positive. That means the velocity is above 0 right there. It's positive velocity. And then I picked a test point bigger than 3. You probably should have picked 3.5 because this was supposed to come to an end at 4. But it doesn't really matter. You get the same result anyway. So I plugged a 4 in. I got a negative. So that means that you have a negative velocity. And then if you look at this sign chart, see, this is what this is saying. This is a graph right here of the position function. And notice what's happening on this position function. The slope of the tangent line, between 0 and 1, the slope of the tangent line is negative. The velocity is negative because you're going downhill, kind of. Okay, then from 1 to 3, the graph starts increasing, so you have a positive tangent line. So think of this like this. Slope of the tangent line is negative. Then from 1 to 3, slope of tangent line is positive. And then once you get past 3, the slope of the tangent line becomes negative again. All right, so basically, you can solve this with an inequality by using test points like that. So I kind of write my solution like this. The velocity was positive from 1 to 3. Okay, and I use parentheses there because at these points, the tangent line is 0 right there. Okay, so the slope is not negative or positive in these two, this low point and that high point right there. So I have to use parentheses so I don't include the 1 and 3. Okay, on this one, 0 to 1, well, this is time equals 0 seconds. Probably on this one, this would actually be the slope of the tangent line right there would be negative. So I could include that with a bracket like that. And then I would exclude the 1. That's what the sign chart showed us, is the velocity was negative. And then 3 to 4. And I went ahead and included the 4 because at 4, the tangent line has a specific value that is negative. Okay, so that's how that problem would work out. Okay, a little bit different situations on that, but similar ideas, certainly. Okay, so I'm going to go ahead and basically I'm going to end the video right here, I decided. And I'm going to do the next part of the video kind of when we start looking at more graphical information on position, velocity, and acceleration. Okay. Hope you enjoyed the video and the Charlie Brown song. I got that stuck in my head now. All right, have a good one.